All right, afternoon, everybody. First time, long time. I know that you've heard Pace at this meeting before, but this is my first in-person OCB. It is rad, by the way. This is cool. So awesome vibe, yeah. So, okay, so why am I here trying to convince you that you need to elevate your senses 400 miles above the sea surface and land surface? I'll do it this way. Oh, man. Sorry, while I'm figuring this out, I should note that I'm a project scientist for the PACE mission, but I'm representing like a ton of different people who have put this all together. So, okay, this is why I'm here presenting that we are roughly 7 months from being on orbit. So coming up with a mission like this is roughly a 20-year endeavor. I can tell you that this mission is old enough to legally drink and deserves to do so, but we are now down to the last 200-something days. So. Update is going to span a bunch of different things. I'll tell you when to tune in and when you can doze off a little, depending on what your interests are. If you do nothing else, I think these are the take-home messages here. First thing, while you're watching our observatory spin, is that this is NASA's next great investment in the combined study of sea and sky. It's also capable of land and terrestrial applications. Its primary reason for being, at least from the major instrument, is ocean color retrieval. So you could do carbon from space. One of my favorite things is to go to some kind of outreach event and try to convince a non-scientist that from 400 miles above the sea surface, I can see microscopic marine algae, which is pretty cool. So, but we're also very capable for aerosols, and we are going to be good for clouds and for land processes as well. The characteristics that you need to know are we will launch in January on a pre-owned Falcon 9. It'll be road tested from Kennedy Space Center. So not too hard from here to go and visit and see a launch from Cocoa Beach. It's a 3-instrument payload. The primary instrument is cleverly called the Ocean Color Instrument. It is being built at Goddard Space Flight Center, and it is standing on the shoulders of predecessors like CWIS, MODIS, and VIIRS, if you're familiar with them. We have 2 smaller Kleenex box size contributed polarimeters, one from the University of Maryland, Baltimore County, and the other from a consortium of organizations in the Netherlands. They are also passive instruments with the difference that they view multiple angles, same footprint on Earth, but from different views, and they have polarized sunglasses on so that you can see different kinds of microphysical properties. When you're super excited and you really want to just dive into this, then you'll come to NASA Goddard Space Flight Center's Ocean Biology Processing Group, the Ocean Ecology Lab, where you would currently get ocean color data to have access. So if nothing else, that's your take-home message here. If you care about the details of instrument characteristics, the next 2 minutes are for you. All right, so we'll do this little visualization and I'll do a voiceover here. So first, you're going to see something that just reminds you we're multiple disciplinary. We should have been place with the L being for land. Like most Earth observing systems from NASA, we're polar orbit, sun synchronous, and 1 o'clock local equatorial crossing time. I mentioned the Ocean Color Instrument is the primary reason for being. It's a hyperspectral radiometer, meaning it measures light continuously from the ultraviolet all the way into the near infrared. So instead of MODIS world, where you only get a couple of wavelengths, you're getting all the colors of the rainbow here. It also has shortwave infrared bands for a number of coastal and aerosol cloud applications. And really importantly, like CWIS and CZCS, it tilts, which I'll comment on a little bit later. One of our polarimeters, HARP2, is hyperangular but multispectral. So only 4 wavelengths of light, but it measures up to 60 view angles. It's wide swath, unlike SPEX1, which is our other one, which is a hyperspectral instrument, but it is multi-angular. So these really complement each other. Instead of one big super polarimeter, you have 2 small mighty ones that really play well together. And all of our footprints here, which I know might be a little disappointing, are on the order of 1 kilometer or more. So we're not going to get into your teeny tiny little river, but still global coverage. We're going to see the whole world every 2 days. Data availability, the latency is pretty good. You should be able to get it within 6 to 9 hours. Thousands of data products, as we'll talk about. And then as we kind of finish up this animation, you'll just get a visual sense of what the swath is going to look like. So I will point out that OCI is going to revolutionize how we view our aquatic world. I think the hyperspectral capabilities are just going to knock your socks off. But it's wonderful to have the two polarimeters as well, too, because they can do cloud and aerosol retrievals far better than you can do with an OCI or a MODIS-like instrument alone. And frankly, from an aquatic point of view, I think the general idea of taking multi-angle polarimetry and applying the methods that you have to do microphysical properties of aerosols and clouds and applying that to hydrosols in aquatic environments is going to be an absolute game changer because the physics is the same for the most part. Okay, so if you don't care about the details and you were tuning out, it's time to wake up. These are the data products. Note that these are passive radiometers, which means they just get a spectral radiance field from the top of the atmosphere. That's all they see. That means every contribution from the atmosphere, from whatever surface you're talking about, and the ocean are all part of that total signal. If you are an ocean aficionado, that's annoying because you got to get the atmosphere out of the way, and that's somewhere between 95 and 85% of your total signal. We have a science team that's very, very good at working together to accommodate all of that. So working from the top down, from atmospheres, microphysical properties, and characteristics of all different kinds of aerosols, including their height and their layers. Similar for clouds, their optical depth, their height, their thermodynamic phase function, which is new, which is going to be really very valuable from the polarimeters, down to the sea surface, where we'll get what the ocean color community cares about, which is ocean reflectances and some other interesting things, including angular light distributions from polarimetry. And there's actually a couple of neat things that you can do with polarimetry, and we think it could be oil slick detection as well as wind speed. Crossing the air-sea interface, you have what we're probably all more interested in, so most of the oceanographers here, light penetration, light available for photosynthesis, all the optical properties, inherent optical properties you could possibly care about. More for this community. The promise of PACE is, of course, metrics related to phytoplankton community composition. So there are a lot of capabilities there. Of course, particulate carbon, suspended matter, things like that. And then in certain parts of the world, we'll actually do bathymetry as well. We have a couple of projects cooking for that. So it's a lot. We are actively engaging with our terrestrial communities as well. It's not a mission requirement, but on a best of effort basis, we're trying to make sure that they're accommodated. Now, again, big spatial footprint, but great precursor hyperspectral information for like new missions, Landsat Next and SBG and so forth. If you really care about everything I just said and you want the details, go online. This is very easy to find on the PACE website. I want to also point out that we're trying to democratize the implementation of algorithms. You don't have to be a science team member to play in our sandbox. We do have a data product implementation plan. That QR code will link to it. If you have a good idea, you have something of interest, you reach out to one of us and we'll do an evaluation of it with you collaboratively. So don't be shy if this kind of thing interests you. And I have a treat at the end, so I'm speeding up a little bit here. Now, if you're super jazzed, there's actually simulated data, so you can start playing with this now. So if you have now been convinced you want to play in this sandbox, there are PACE data products, and they are inclusive of the geophysical products at the sea surface and at the atmosphere, but also the top of atmosphere radiances. And this would give you some sense of data volumes and so forth that you will have to deal with. I will note that there's also simulated data for both polarimeters too, if you are interested in that. They can be found following that QR code. Okay, so now if you're just curious what happens in the last 200 days of launch, here's where we are. So there are, generally speaking, two different kinds of tests you do to get ready for launch. You have the launch environment itself, so you have a lot of mechanical tests. Basically shake the crap out of this thing. So it is mechanical environments where you're doing vibration, acoustic, and shock tests to simulate what launch is actually like. We've completed this, and I'm proud to report nothing major broke. Then you do the space environment. And so in this case, you need a thermal vacuum or thermal balance chamber where you get down to zero pressure like you would have in space, like a vacuum. And then you do a wide range of thermal tests to make sure that you understand instrument performance. You need a wide range because of the way your orbit actually happens. Doing a little bit of yoga here, you have the solar panel side, which is always seeing the sun, so it's very, very, very hot. Then you have the side that's on the other side that never, ever sees the sun, and it's very, very, very cold. So there's this gradient there, and you need to test all of those things. Right now, they are actively depressurizing the thermal balance chamber to start 2 months of thermal vacuum tests. Simultaneously, of course, we're pushing all the bits through the system. In early November, probably just after Halloween, they're going to put our observatory on a truck and make the ride to Florida. I recently learned the logistics of all of this. If you want to get together at the dinner tonight, it's fascinating. It's like Smokey and the Bandit. It is so cool. So, and then at the processing facility, it'll be about 50 days of work where everything gets recharacterized in a special facility that's not too far from SpaceX. So what can you expect once we finally do launch? There's 60 days of in-orbit commissioning. The first 30 days or so are related to just orbit maintenance, making sure that the spacecraft is doing everything that it needs to, and then you turn the instruments on. And they take a while to off-gas and things, so you don't really do instrument work the first 30 days. Second 30 days, then you do all the instrument checkout. We're really hoping for the January launch that we can do first light within this period right around the Aquatic Sciences meeting. We feel like that could be a pretty fun party. So, launch plus 2 months, once this IOC is over, data will become publicly available to all of you, maybe even sooner, depending on how things go. First batch of data coming out will be all of our heritage and required data products. So things that the agency is requiring us to put out, like a hyperspectral radiance field, aerosol optical thickness cloud properties, and then anything that we can do with MODIS and VIIRS. And then within weeks to a month or two, we'll have all of the advanced products come out as well. And the reason for a slight delay is just verifying that things like remote sensing reflectances are good enough to actually get to viable community composition metrics and so forth. And then we have a 3-year prime mission life with 10 years of fuel. We're expecting there to be a number of 3-year mission extensions to follow. The design, where I say 3 years, is really just a technical engineering design for parts reliability and redundancy. I mean, we have tried to beat into engineering's head. This has to be a 15 to 20-year mission. You don't do climate with 3 years. Okay, so now you're all super intrigued and you want to know how you can get involved. There's a couple of different ways. The first, shout out to our applications program. They are spectacular. If you haven't been to one of our virtual applications meeting, there's one coming up in September. It is open for registration now. Highly recommend it. Through applications, you can either join a community of practice, which would get you access to newsletters and meeting invites and just general things that we talk about, or consider becoming an early adopter. And we have like 27 good projects already within the early adopter community. Maybe of more interest is sometime in the next 2 months, there will be a ROSA solicitation for the 3rd PACE science team, and that will be looking for fun and engaging applications of the mission. So that might be of interest to a few of you. Not all we can say about that right now. For those of you who are really interested in instrument technology, we have 2 ongoing projects related to what we call system vicarious calibration. For the uninitiated, this is basically an instrument, some more systems that are used for our absolute on-orbit calibration after launch. They're radiometers, but they're very, very neat. One is HyperNav. We've already talked about like BioErgo. This is basically a radiometer on a float like that. Hopefully they will commercialize because that could be a great instrument for our community. The second is a permanent mooring, 3-armed mooring that, if you've heard of the MOBI instrument, it builds on that legacy. It will be deployed off the coast of Australia, and these are going to become our calibration sources. But what might be of larger interest is these data streams are also publicly available. And so if you have interest in radiometry or the light field at any of the sites they're deployed, that might be of value to you. We are currently getting ready to convene a panel for a post-launch validation science team. More on that soon. There will be a post-launch airborne experiment as well. So a lot of data coming your way. Earth data policy is that this all becomes publicly available as soon as possible. In fact, we baked in for the validation science team data has to be turned around within like 60 days. You want to learn more because this is amazing and I'm out of time, then start at our website or our social media landing pages. The website is great because it has fun stuff, it has outreach, but it also has a series of technical documents that really get into the guts and the deep end of the pool of everything that we're doing. So if you have any interest in why the instrument designs are what they are, that's the place to go. You want to learn more about this whole discipline because it's amazing. Oh, damn it. because it's amazing and we've intrigued you, then I'd like to give a wonderful shout out to our OCB collaborators and colleagues. They supported and basically helped create a class based on PACE that we hosted last August. It was roughly just shy of 50 students from the US and 6 or 7 other countries that converged in Maryland. And we spent a week taking a very, very deep dive into the backstory of the mission. Everything we produced for this is available online. So all of our lectures were recorded. All of the PowerPoints should be available there too, which is, you know, how this wonderful organization operates. So if you want to learn a little bit more, you're teaching classes, that is a great place to start. If you can't find anything you're looking for, contact one of us and we'll make sure you get it. So wrapping this all up, and then I'm going to steal 2 more minutes. Moving from multispectral radiometry to hyperspectral radiometry, quantum leap, and how we're going to view phytoplankton community structure. There are some other wonderful hyperspectral instruments. We're the only ones with 1 to 2 day global coverage planned here or abroad. So really a global perspective on how our home planet is changing. Great things for atmospheres, wonderful polarimetry, great proof of concept. Tilt is essential. You care about tilt because every 2 days you will see 17 million more kilometers of ocean than you would see otherwise. For context, that's the size of South America. Where does sun glint happen? The equator. What else happens at the equator? You're smarter than I am. You know all of this stuff. Okay, and then last, and I'm sorry to everybody, but this is the coolest thing that happened to a lot of us in a long time. That is the U.S. Marine Band. So that's the president's own band. And our mission systems engineer came up with this idea because he's a big brass fanatic, that can a band of that quality play louder than a rocket launch? And so they came in, they went into our acoustics chamber and played as loud as they could. And they did Star Wars and they did Jaws and they did wonderful things. And all of this will be available if you have any interest in hearing it. Why I'm sharing it now is that they went out of their way and the Marine Band composer created a fanfare for the mission. It's only 2 minutes long if I can indulge you in this. I don't know if audio will work.
That's one way to up your launch.
So, all right, that's the update. What's up in their plan?
For those of you who haven't engaged with PACE, but you want to engage with PACE and you're excited about it, we did a training course last summer, and I really encourage you to check out the website. It's on the OCB website under training activities, and all of the lectures were recorded. All of the PDFs of the lectures are in there. There's so much material in there, and it was a really valuable experience for everybody. So you can go in there and steal stuff for your own lectures if you want, or you can learn more about the mission itself.